video to help you through the activity on triglycerides and dietary fats. Triglycerides are the molecules that we know as oils and fats. So next time you're using oil on your salad, remember these molecules. Before we talk about triglycerides, I want you to remember condensation and hydrolysis reactions. A condensation reaction is a reaction that takes two units. It removes an OH group from one unit and a hydrogen from the other unit and makes water. At the same time, it makes a new bond between the two original units to make one larger unit. This is a condensation reaction. A hydrolysis reaction is the opposite. Take two units joined together by a bond and cut that bond using water. OH from water will go to one side of where the bond used to be, and hydrogen will replace the bond on the other side. Hydrolysis literally means to cut with water. Hydra means water, and lysis means to cut. We saw this originally when we talked about condensation and hydrolysis of saccharides. Here are two monosaccharides, which can be combined into a disaccharide using a condensation reaction. Notice that the alcohol from the anomeric carbon is removed, and the hydrogen from another alcohol is removed to form water. The carbon that loses its OH group is also the carbon in the molecule that has the most bonds to carbon. In this case, it's an anomeric carbon. Whichever bond loses a bond to oxygen gains a new bond to oxygen in the product. This new bond in a disaccharide is called a glycosidic bond. And it's also the bond that you cut when you do a hydrolysis reaction. In a hydrolysis reaction of a disaccharide, you cut the glycosidic bond. The anomeric carbon is the carbon that has the most bonds to oxygen, and it will lose this bond. That bond will be replaced by an OH group on the anomeric carbon, and the oxygen of the other molecule will gain a hydrogen. Hydrolysis literally means to cut a bond with water. Now we're going to see these two types of reactions applied to triglycerides. It's actually three simultaneous condensation reactions that form a triglyceride. Here I have a cartoon of three fatty acids where I've just represented my fatty acid tail with a bubble. But the important part of the fatty acid will be the carboxylic acid because this is what is reactive. Notice that the carbon here has three bonds to oxygen. And these carbons are going to be most reactive. I also will take a molecule of glycerol, which contains three alcohols. Each of these alcohols will lose its hydrogen, and its hydrogen will be combined with the OH group on the carboxylic acid to form water. I will form three molecules of water from the three reactions that will occur. In the condensation reactions that happen here, I formed a new bond between the original oxygen of glycerol and the carbonyl carbon of the fatty acid. Water is formed as a byproduct, and since I did three reactions at once, I get three water molecules. Please notice the color coding on this diagram. It's meaningful, and it shows you where the atoms have come from and where they've gone. So study it well if you want to understand what is happening in this reaction. A condensation reaction to form a triglyceride involves three alcohols and three fatty acid groups. And the product will be three ester functional groups. The new ester bond between the carbonyl carbon and the oxygen is the new bond that forms. And when you do a hydrolysis reaction on this, that would also be the bond that is broken. Now that we've seen the cartoon version, let's look at this reaction with real chemical structures. Here we have a glycerol molecule and three fatty acids. If we're going to combine these in a condensation reaction, we remove the OH group from the carboxylic acid and the hydrogen of the alcohol groups of glycerol to make water. And then we will make a new bond between the oxygen of glycerol and the carbonyl carbon of each of the fatty acids. The product is a triglyceride and three water molecules. Notice that the fatty acid tails have not changed at all over the course of this reaction. So whatever fatty acids you started with, you would get those in the triglyceride products. I'd like to point out that we've changed the properties of the molecules. In the reactants, glycerol is fully soluble in water, and fatty acids are partially soluble because they're amphipathic. Our products are water, which obviously would be soluble in water, but a triglyceride is so nonpolar that it is not soluble in water. Even though it contains esters functional groups, which are polar, it is overwhelmingly nonpolar because of the 3 fatty acid tails. So the 3 fatty acid tails overwhelm the properties, and this is mostly nonpolar. Associate the word triglyceride and this structure with oils and fats, because you know from experience that oils and fats are not soluble in water. So you know that this molecule is not soluble in water, even though it has some polarity in its molecule. Mostly nonpolar molecules will still not be soluble in water. Now let's look at the hydrolysis reaction. Here's a cartoon version, and the ester bond that was formed in the condensation reaction is the same one that you would break in a hydrolysis. You can see that this is the part of the molecule that came from glycerol, and here's the part of the molecules that came from the fatty acids. When you break the bond, the OH group from water goes to the fatty acid part to give you carboxylic acids, and the extra hydrogen will end up on the glycerol molecule to give you 3 alcohols. Please notice the color coding on this slide because it shows where all of the atoms have come from and where they have gone. It's helpful to understand how atoms move around in these reactions so that you know how to draw them. Now let's look at a hydrolysis reaction using real chemical structures. Here's a triglyceride molecule plus 3 water molecules, and we will draw the products of this hydrolysis reaction. When I draw the products, I will cut the bonds of the ester functional group. It's the bond between the oxygen and the carbonyl carbon. When I cut that bond, I will add the hydrogen, one of the hydrogens from the water, to each of the alcohols, and the OH group from water will end up being bound to the carbonyl carbon. When I hydrolyze a triglyceride molecule, my products are always glycerol and 3 fatty acids. Make sure that when you draw these reactants and products, that the same fatty acid tails are in your reactants and in your products. Nothing about the fatty acid tail has changed. The only change has been in the ester functional group going from an ester to alcohols and carboxylic acids. There are several ways you can draw triglycerides. The way that I've drawn it in most of my slides is with the fatty acid tails off to the right, but I could also draw them all off to the left. I could draw them in many different directions. The last 2 examples here are really more realistic of how the actual molecule exists when it's in an oil solution. And perhaps these are more telling as far as their polarity goes. There are nonpolar chains in all directions, and only the very center of the molecule is slightly polar. And this is why the molecule is overwhelmingly nonpolar and it is not soluble in water. There are several different ways you can represent these triglycerides, so don't let it throw you off if you see them represented in different ways. Now let's talk about the difference between fats and oils. Both of these things are triglycerides, but fats have more saturation, or they have more hydrogen atoms. The word saturated refers to the number of hydrogen atoms. Here's a fat that only has 1 unsaturation. This oil, on the other hand, has many more unsaturations. Or, in other words, it has more double bonds. Every time a double bond is formed, you remove 2 atoms of hydrogen. The word saturated or unsaturated refers to saturation with hydrogen or unsaturation with hydrogen. Saturated meaning you have as many hydrogens as possible, and unsaturated meaning that you don't have as many hydrogens as possible. Fats have less double bonds than oils do. And this leads to different physical properties. Fats are more flexible than oils, and that means that they can stack better in solid structures. Butter is a fat, and so is lard and Crisco. These things are solid at room temperature. On the other hand, many of our oils are liquid at room temperature, or they have very low melting points compared to fats. Oils are liquid at room temperature because they don't stack as well in a crystal structure. And these cis double bonds in an oil kink the fatty acid tail. The kinks in the fatty acid tail reduce the intermolecular interactions through the London forces of the hydrophobic tails. Oils are usually liquids, or they have lower melting points than things that are fats. And fats are normally solid at room temperature. Fats and oils are both in food products, and they both contain some unsaturation. The cis double bonds in fats and oils are reactive with oxygen in the air, and the reaction with oxygen is what makes fats and oils go rancid. Oxidation, or reaction with oxygen, is how oils and fats go rancid. Here's a reaction that's showing you what can happen when oxygen reacts with a cis double bond. In this slide, I've written a shorthand version showing just one of the fatty acid tails of a triglyceride, and the other two fatty acid tails are just abbreviated with R. I want to focus on just this double bond. The oxidation reaction that causes foods to go rancid is basically an oxidation where this double bond is completely broken and the carbons become double bonded to the oxygens from the oxygen molecule. This happens because cis double bonds are particularly reactive. And the products here, these small molecules that are released, are stinky. Eating these foods is not necessarily bad for you, but it's not very pleasant. This is why we put nuts and butter and lard in the refrigerator to store it for long term. It's so that this reaction does not happen as quickly and our foods will stay fresher longer. Food manufacturers don't want this to happen though, and they don't really want to have to refrigerate all of their foods. And so food manufacturers have developed techniques to get rid of this problem. The way they do this is through a reduction reaction. They can actually get rid of the cis double bond, or they can convert it into a trans double bond, which is less reactive. If you add exactly enough hydrogen to react with each double bond, you can get rid of the double bond through this reduction reaction. There is one hydrogen added to each side of where the double bond used to be. This reaction is reversible, but when the hydrogens are removed again, it actually doesn't reform the cis double bond. Instead, it reforms a trans double bond. So the double bond can be removed and then reformed, but when it is reformed, it's now a trans double bond. And this is less reactive than a cis double bond, and this one is not reactive at all. It's to the oxidation reactions that cause foods to go spoiled. So chemists in food companies can change the properties of oils and fats to avoid rancidity. Complete hydrogenation is when you add enough hydrogen to react with each one of the double bonds completely, and you remove all double bonds completely, leading to all single bonds. This is one way that oils can be converted into fats. On the other hand, if you still want the food to be an oil, you can do partial hydrogenation. This is when you don't add enough hydrogen for all of the double bonds to react completely. So some of them will react, but then they'll go back to double bonds. And so in this reaction, I've shown that a couple of the double bonds have reacted completely, but some of them have been converted back to double bonds. In this kind of reaction, when you do partial hydrogenation, any double bonds left over are now trans instead of cis. Although this is advantageous for food manufacturers who want their oily foods to have a long shelf life, these trans fats have been found to be very bad for human health. If you want to avoid trans fats in your diet, make sure you check the ingredients labels on your foods. If it says that there are partially hydrogenated oils in the food, that means that there are in fact trans fats in that food, even if the nutrition label says that there are not. Partially hydrogenated oils will always contain trans fats. Okay, now please try to complete the entire activity and check the key to make sure that you're correct. Thanks for watching this video on triglycerides and dietary fats. If you have any questions, please post them in the comments and let me know if this video was helpful.